In the past few videos, we've been talking about different number systems, and in this supplementary video, I'd like to show how we can go beyond the real numbers and talk about new numbers, such as the complex numbers. This idea of constructing new number systems permeates beyond pure math into applied math, where one often constructs a new number system if you're interested in modeling some sort of new phenomenon. For example, rotations are very important in physics, and the complex numbers and quaternions have a lot to say about rotations. And you can even go beyond that. You can talk about octonions and higher dimensions as well. Now, in the context of the complex numbers, one's often introduced to the complex numbers by supposing that there's some fake real number, which we call I, which has this property that when I take the square of I, that becomes -1. And I call this a fake real number because, of course, as you've learned in your math education, no actual real number has this property that it squares to -1. But essentially what we're doing here is we're supposing that such an object exists, and algebraically what it's going to do is it's going to serve as a placeholder when doing calculations. That's to say that whenever I see the quantity I squared, I can replace that with -1, and vice versa. Whenever I see -1, I can replace that with I squared. So it's serving an algebraic function more than serving as an actual real number that squares to -1. And in this video, what we're going to do is we're going to show how one can easily construct the complex numbers from the real numbers. When working with the complex numbers, we often notate this in a plus bi form, where a we call the so-called real component of the complex number, and the b is the imaginary component. So this very naturally leads to this idea of representing complex numbers as ordered pairs. And ordered pairs leads very naturally to this notion of the Cartesian product. So what we're going to do is we're going to define the set of complex numbers as just r times r. Or sometimes you'll just see this written as r squared or r2. For example, if we have some element within r times r, for example 1, 2, we might commonly write this as 1 plus 2i, where this first component is going to be the so-called real component, and the second component is going to be the imaginary component. So by 1, 2, what we might say is 1 plus 2i, that means 1 plus 2i. And by 1 plus 2i, what we really mean is 1, 2. So this is no problem from a set theoretic point of view. We're just taking the Cartesian product between the set and itself. So this set certainly exists. There's no problem there. But beyond defining the set, one wants to do some algebra. We want to investigate the algebraic structure of this set, and also we want to be able to do some computations with these complex numbers. In an informal sense, we essentially already know how to add and multiply complex numbers, but let's go through what one normally does when doing those operations. So let's say we had the complex number 1 plus 2i and also 2 plus 3i, and let's add the two. Well, that's very simple. We just look at the sum of real parts, which is 1 plus 2. That gives me 3 for the new real part. And then we look at the sum of imaginary parts, so that'd be 2 plus 3, which gives me 5i. So the result of that computation is 3 plus 5i. More generally, let's say we had a plus bi and c plus di, and we wanted to add the two. So same thing, we just add the real parts. That gives me a plus c for the real part, and then b plus d for the imaginary part. So I get a plus c plus b plus di. And same deal for multiplication. We essentially know how to do this already. So same example, so let's multiply 1 plus 2i and 2 plus 3i. So for the real part, we have two terms when we distribute here that are going to give us a real part. So we're going to have 1 times 2, that gives us 2. But we also have this 2i times 3i here, which will give me 6i squared. And since I squared serves as that algebraic placeholder, I replace I squared with -1. So I get 2 minus 6, that gives me -4 for the real part. And going back here, I have two terms that will give me an imaginary part. I have 1 times 3i, or 3i, and I have 2i times 2. So when I sum those two, I just get 7i. So the result of this computation is -4 plus 7i. And more generally, if I'm just multiplying two complex numbers, a plus bi times c plus di, I do the same sort of thing. I look at the two terms that pertain to the real part. I have the a times c here, but I also have the bi times di here. So I get, for the real part, ac plus bdi squared, and that's going to become AC minus BD, that's written right here. And for the imaginary part, I have two terms as well. I have A times DI and also BI times C. So when I sum those, that'll give me AD plus BC times I. And now our informal computations are going to lead to our formal definitions for what it means to add and multiply two ordered pairs. So let's say I have two ordered pairs, AB plus CD. We're going to define addition between the two as we did up here. So the real part, or the first component, is going to be A plus C, and the second component is going to be B plus D. So I just add component-wise, like so. So that's pretty intuitive for addition. But for multiplication, this is going to be a much more interesting operation. So again, we're going to use our informal computation up here to come up with our definition. So what we mean when we multiply two ordered pairs, AB times CD, is going to be the following. The first component is going to be given by AC, and then minus B times D. So it's going to be the first component. And then the second component is going to be A times D plus B times C. So you can see this is going to be a much more interesting operation. And really the multiplication is going to give rise to a lot of interesting properties for these complex numbers. So now that we've said what addition and multiplication mean for complex numbers, let's start to investigate the algebraic properties of these definitions. So let's deal with addition first. And from our experience of other number systems, there are a number of properties that we might be interested in. For example, the commutative law, the associative law, distributive law, and so on. So let's see whether the commutative law for addition holds. So for that to hold, it must be true that AB plus CD gives the same result as CD plus AB. And you can check for yourself that this indeed holds, and this comes from the very intuitive definition for complex number addition. So the commutative law is going to hold for complex number addition. And furthermore, the associative law for addition is also going to hold, that if I have three numbers, AB, CD, and EF, it doesn't matter in which order I do the addition. I could do AB plus CD first and then add that result to EF, or I could do CD and EF first and then add that result to AB. And again, you can check for yourself that the associative law is going to hold for complex number addition. Furthermore, the closure property is going to hold. That just means that when I take two complex numbers and I add the two, what I get as a result is another complex number. So adding two complex numbers gives a result that stays within that set. So that's closure. I also have the additive identity. That is, I'm looking for some element in this set such that when it's added to AB, it doesn't change it. It just gives me AB back out. And you can see for yourself that the element 0, 0 is going to be the additive identity of this set. So I take AB plus 0, 0, and that just gives me AB right back out. So the element 0, 0 is going to be the additive identity. And lastly, I might be interested in additive inverses. That is there some other element in this set given AB such that when I add that thing to AB, it'll give me the identity, which is essentially the 0 element of this set. And again, you can verify for yourself that given any complex number AB, if I add negative A, negative B, that'll sum to 0. That'll sum to the additive identity. So what that means is that every element of this set, AB, has a negation, which I would call negative A, negative B. We can see that addition has a very nice structure in the complex numbers. So let's now investigate multiplication, the algebraic properties of multiplication. So again, we have these properties of interest, such as the commutative law, associative law, etc. Since our definition isn't as intuitive, these laws aren't as obvious as they are for addition. But let's go through them and show how they can be proven. So let's see if the commutative law for multiplication holds. So again, if this commutative law holds, it must be true that AB times CD is the same thing as CD times AB. And now we just apply the definition for multiplication of two complex numbers. So on the left-hand side, I get AC minus BD as the first component, and then the second component is going to be AD plus BC. I apply the definition to the right-hand side, so I get CA minus DB, CB plus DA. And since I know for the real numbers, addition and multiplication are commutative, I could just switch all this stuff around. So instead of CA, I can write that as AC, DB, I can write that as BD. And I can switch the order of these two. And I can also switch the order over addition. So I can write this entire second component as AD plus BC. And indeed, we get equality between the two sides. So we can see that the nice properties of the real numbers give rise to at least some of the nice properties so far of the complex numbers. So we can see here that the commutative law for multiplication holds for the complex numbers. And as an exercise, I think you should verify for yourself that the associative and distributive law holds for multiplication. And again, this is just multiplying out these numbers. Just apply the definition. You'll see for yourself that the associative and distributive law will hold. And just to remind you what the associative law is, so I have three complex numbers, A, B, and C. The order in which I multiply them doesn't matter. I could do A, B first, and then multiply the result times C. Or I can multiply B and C first, and then multiply that by A. And then the distributive law, that's pretty obvious. Some of the more interesting properties for multiplication, we might be interested in seeing whether there's a multiplicative identity. That is, that there's some number in this set, such that when I do AB times that number, I get AB as a result. And I claim that the element that has that property is 1, 0. And let's verify that. So what I'm saying is that AB times 1, 0 should give me AB as a result. So I do A times 1 minus B times 0. So it gives me A as the first component. And I do A times 0, that's 0, plus B times 1. So it gives me B. So I can see that 1, 0 is indeed the multiplicative identity. And lastly, we might be interested in seeing what the multiplicative inverse is. That is, given a number AB, I want to find some other number, let's call it CD, such that AB times CD gives me the identity, 1, 0. So let's find that multiplicative inverse. Here I have the statement for the multiplicative inverse. That is, if I'm given some number AB, I'm asking what number CD has the property that AB times CD gives me the multiplicative identity, 1, 0. And now for this, I just apply the definition for complex number multiplication. So I get AC minus BD, and that must be equal to 1, since equality between ordered pairs means that the components are equal to one another. So I get AC minus BD has to be equal to 1. And then for the second component, I get AD plus BC has got to be equal to 0. So that's written here. And instead of that order, I just flip the order. I write it as BC plus AD, and you'll see why in a second. And that's got to be equal to 0. So I have this system of two linear equations. And I'm assuming that AB is a given, and I'm looking for CD. Now, I line up these two just to make it obvious that this is just a technique of linear algebra. This can be solved using linear algebra. So written in matrix form, this might be written as A minus B, B, A as my coefficient matrix. And then my unknowns would be the vector CD. And the result of that has got to be the vector 1, 0. So this is just a matter of solving a system of linear equations for C and D. And it turns out this system has a unique solution when the determinant, it's called the determinant, which is going to be a squared plus b squared is not equal to 0. So if you do this calculation, you solve for C and D, you'll find that C is going to be equal to a over a squared plus b squared, and D is going to be equal to minus b over that same denominator, a squared plus b squared. And it's no coincidence that this denominator is like this, a squared plus b squared, because it's the determinant of this matrix. So you can verify for yourself that the multiplicative inverse for AB is going to be this ordered pair. That is to say, when I multiply AB times this ordered pair here, I should get 1, 0. And you can verify that computation for yourself. In terms of writing out the multiplicative inverse, we might write this as AB minus 1, which is going to represent the inverse of AB. So we might write it like this, AB inverse equals that ordered pair that we just found. To take a numerical example, let's say we want to find the inverse of 1, 2. So I'm looking for 1, 2 inverse. So I just apply this formula here. First, let's look at a squared plus b squared. So that's going to be a sum of squares of the components. So I get 1 squared plus 2 squared, which gives me 5. So 5 is going to appear in the denominators here. And then in the numerator, I get a. So I'm going to leave that first component there. And I have negative b instead of b. So it's going to be negative 2 over 5. So we see that the inverse of 1, 2 is going to be 1/5, negative 2/5. Now, going back to the way that we're sort of used to doing complex number arithmetic, this might be written as 1 plus 2i inverse, which might also be written as 1 over 1 plus 2i. So how do we normally do this computation? How would I normally write 1 over 1 plus 2i in a plus bi form? Well, what I do is I multiply both top and bottom by the conjugate of 1 plus 2i, which is 1 minus 2i. So in the numerator, I just get 1 times 1 minus 2i, so I get 1 minus 2i here. And then I get 1 plus 2i times 1 minus 2i. So I distribute there, I'll get 1, now I get minus 4i squared, or 1 plus 4, which gives me 5. And you can see here, this works out very nicely, gives the same result as we got up here. And I get 1/5 minus 2/5 I. So in our talk of complex numbers as just ordered pairs, we no longer have to make any reference to I. We really don't have to talk about the imaginary unit anymore. We sort of abstracted that away and we're just dealing with ordered pairs now. But just for interest, where does this imaginary unit I fit into all of this discussion of ordered pairs? So one observation that we can make is that we notice that the ordered pair 1, 0 behaves very similar to 1 in the real numbers in the sense that they're both the multiplicative identity. And furthermore, just by negation, the object negative 1, 0 behaves very similar to minus 1 in the real numbers, since they're both the negative of the multiplicative identity. So what we're going to ask in answering this question, where does the imaginary unit fit into all of this? Is there a complex number, AB, is there some object AB which squares to minus 1, 0? And notice this is essentially asking the question, is there some object which squares to minus 1? So we're looking for this number AB such that when I square or multiply by itself, that gives me minus 1, 0. So let's just solve that. So again, we just apply a definition for multiplication. I get a squared here minus b times b, or b squared. So I get a squared minus b squared equals minus 1. And then for the second component, I get a times b plus b times a gives me 0. So I have the second equation, 2ab equals 0. So again, I'm looking to solve this system. Here it's not a linear system, but we can still solve the system for a and b. Now from the second equation, 2ab equals 0, which means that ab equals 0. So that implies that either a is equal to 0, b is equal to 0, or both. So it's got to be one of these three possibilities. Now it can't be both, because then I would get in this first equation that 0 is equal to minus 1. And furthermore, it can't be the case that b is equal to 0, because in this first equation I would be getting a squared is equal to minus 1. And there's no real number that squares to minus 1. So that means that only a is equal to 0. So that immediately tells me that if such an object AB exists, its first component is going to be 0. So let me substitute a equals 0 into that first equation. That's going to give me minus b squared equals minus 1, or b squared equals 1. And in the real numbers, that has two solutions. B can be equal to 1 or minus 1. So that means I found two ordered pairs that square to minus 1, 0. Those would be 0, 1 and 0, minus 1. So essentially what I found here is the representation for I within the complex numbers. So what we're saying is that 0, 1, the object 0, 1, essentially behaves like I. That is, when I square it, it gives me the object that behaves like a minus 1. And I've also found two objects that have that property. So I might define 0, 1 as I, and I might define 0, minus 1 as minus I. So we've essentially found the representatives of I within the complex numbers. The reason complex numbers have stood the test of time and have persisted in pure and applied math is because they have a lot of nice algebraic and geometric properties. In terms of the operations that we've just defined, the addition and multiplication operations, they have very nice geometrical interpretations. So addition with the complex numbers is nicely interpreted as vector addition. And multiplication is very nicely interpreted as scaling and rotation operations. Let me give you an example of a scaling operation. So let's say I had the complex number AB, and I multiply it by 2, 0. Now 2, 0, this object 2, 0 is very similar to the object 2 in the real numbers. And what happens when I multiply by it? I get the vector 2a, 2b. So what's the relation between 2a, 2b, and the starting element, ab? Well, this is just a scaled element, meaning that this object that I get out of the operation has a length which is double the initial vector. So elements that look like this, like 2, 0, 5, 0, 20, 0, these act to scale a vector, to increase or decrease the length of a vector. And furthermore, there's an object in the complex numbers which encodes the transformation of rotating counterclockwise by 90 degrees. And that object is really I. It's the object 0, 1. So when I take a vector, AB, and I multiply by 0, 1, or I, what I end up getting is negative b, a. And if you remember from your high school transformations, what's the relation between AB and minus b, a? Well, that's just a 90-degree counterclockwise rotation of a vector. So what I see here is that multiplying by I is going to transform this input vector AB by rotating it 90 degrees counterclockwise. And in the most part, when I multiply by some arbitrary complex number, the action of that complex number is going to be some combination of scaling and rotation. To give you an example of that, let's consider the complex number 0, 2. Now I make the observation that 0, 2 can be written as the product of 2, 0 and 0, 1. And just from our investigations up here, we know what the action of those two numbers are individually. So what that means is that the complex number 0, 2 is going to be the composite of the two actions. So I know that 0, 1 rotates 90 degrees counterclockwise, and 2, 0 scales by 2. So what that means is that the action of 0, 2 is going to be both. It's going to be rotation by 90 degrees counterclockwise and scaling by 2. So you can see how we can start to compose operations here. We can talk about both scaling and rotating a vector simultaneously. Now what I say in this video is just scratching the surface on the properties of the complex numbers. And if you're interested, there's a whole field of study called complex analysis, which studies the complex numbers. But let me close this video with one more interesting fact about the complex numbers. Now, instead of thinking of a complex number as an ordered pair, I can also represent a complex number as a 2x2 matrix in the following way. Instead of writing AB, what I do is I stick that first component in the diagonal entries of a 2x2 matrix, and then I stick the second component in the 2, 1 position, in the second row, first column position. And then for that final entry, in the first row, second column position, I put negative b in that position. For example, the complex number 2, 1 would be represented as 2 minus 1, 1, 2, as a 2x2 matrix. Now, what's nice about writing it in this way is that I don't have to define any new operations. So addition and multiplication for complex numbers written as a matrix is just matrix addition and multiplication. For example, if I wanted to multiply 2, 1, 0, 1, I can first write them as matrices. I would write 2, 1 as 2 minus 1, 1, 2, as I did up here. And I would write 0, 1, or essentially I, as 0 minus 1, 1, 0. And then I just do conventional matrix multiplication to find the result. So when I multiply these two matrices, I get the matrix minus 1, minus 2, 2, minus 1, which then I essentially convert back to the order pair representation. So this would just be the order pair minus 1, 2, which is right here. So we can see what's nice about this is that I don't have to talk about any new operations. I can just say, okay, complex numbers are just special 2x2 matrices, and then if you know how to multiply two matrices, you understand how to multiply two complex numbers. So that's just one more interesting fact. And as I said, I just scratched the surface of complex numbers in this video. But hopefully you've enjoyed this discussion of complex numbers and how we can extend our concept of number beyond the set of real numbers. So thanks for watching.